Okay, in this video, we're going to talk about how we draw linked list operations and just figures that represent a linked list in general. So drawing a linked list is important because it's one way that we can think about how they work, and it's also a way you can demonstrate that you know how it works. And it just tends to be the case, I find, that when I'm working on code and I need to think more carefully about how a data structure manipulation is working, I might sit down and draw it out on paper. And so the purpose of this video is to talk more about how you can do that in kind of a formal and precise way. There are lots of ways you could do this. The way I'm showing you is one way. It may not even be the best way for you, but it's a pretty good way. And there are some details you just need to be really precise about and really careful about whenever you're drawing pictures of code and you're trying to think more carefully about code. And so part of it is to get us on the same page about what some of those details are, so that when you're looking at my drawings, you understand what I'm showing you. And also, more generally, I'll just say that representing code visually is a common tactic for documenting how code works. And there are lots of systems out there for creating visual representations of code. So it's not only like something good to do right now, but it's something you're going to see in one form or another over and over again as you learn more about software. Okay, so drawing linked list specifically, there are some rules I'm going to tend to follow when I show you a picture of a linked list. And this will also apply down the road as we draw other data structures. So when I want you to know that something is an object, I'm going to tend to draw it with a box. So for example, the list object, I'm drawing with a box around it. And then inside the list object, there are a couple of fields, head and tail. And head and tail are of the same type. They're both list node pointers. And since it would be hard to tell apart these fields if I didn't tell you what they are, I'm going to put their names in here. And that allows me to distinguish them. And another thing I'm going to do, though this is fairly optional, is whenever I have a pointer, I'm going to put a black box inside the pointer field. And that way you know that there should be something coming out of that box. An arrow should be coming out of such a box. Pointers always include a box, and then we're going to show the relationship between a pointer and what it points to using an arrow. Here's a different object. This is the list node object, and you'll note that to show you that it's not a list, that it's a list node, I put the name of the class in here. I could also optionally put a name of a variable in the source code in order to make it clear which object I'm referring to, because I might have lots of copies of these. I might have multiple lists, I might have multiple list nodes, and so then differentiating them with some sort of variable name either inside the box or beside the box can become valuable. List node has two fields. One is a list node pointer called next that of course has this black box in here to indicate it's a pointer. And the other one is a data field. And because it's a data field and it's not a pointer, I don't really need the label to make that clear. If I put something in here in quotes, that's obvious that it's a string. And so, at least for this particular case, I'm not going to label the data because it's clear. And I put the next here just because in some of the discussion, I want you to remember that that field is called next. Okay, as I've said before, pointers are going to be represented with an arrow. It represents the link between a pointer and the object it points to. And if a pointer is pointing to null, then I'm going to show that arrow pointing to a label called null pointer. It may be a little weird to show an arrow going to null pointer, but that way I'm always consistent. A pointer always has an arrow, and if it's a null pointer, then it's pointing to this null pointer label, or possibly the null, just null. I might just write null, which means the same thing. Okay, and then if I have a local or a temporary variable that's just a pointer and it's just pointing to an object and it's not inside of an object, then I may just, write it this way. So I'll just write the name of that variable with an arrow coming out of it. And that lets you know that that's a variable, that's a pointer, that's pointing to some object. So let's look at some examples of how we use this. So let's say I want to draw a picture for this code. I create a variable called temp and I set it equal to a new list node object. And just as a refresher, we define our list node this way. I replaced item here from a more generic item type to specifically be a standard string, just to make this example a little more clear. But this item could be anything. It could be an integer, it could be a string, we could make it whatever, and then we'd want to draw our object to reflect that. But here we're going to assume it's a string. We also have this next pointer. So when I call new list node, we know that a list node object is going to be made in the heap. And there's nothing here that tells you this is the heap. I'm not going to label where things are in memory most of the time, but I do need to show, oh, there's this object now that's been created. It's a list node. It has a data field that's initialized to the string data. And then it has a next field, and you'll see over here in the constructor, I initialize it to null. So this next field is pointing to null pointer. And then this object, the address of this object is stored in this variable temp. And so I'm showing that the temp variable is pointing to this list node object that's somewhere in memory. Right? I don't need to know exact addresses to be able to draw a picture like this, because it's meant to be implied that list node is an object that's somewhere in memory. It contains this data string. Its next pointer is null. And I have this local variable temp that's pointing to it. And this tells me pretty much everything about what this line of code is doing or has done. The other thing I want to point out is that this temp variable, it points to this outer box, because this outer box is the list node itself. I don't draw this arrow going inside and pointing at data or pointing at next, because that would be wrong. Those fields inside aren't the object as a whole. Temp points to the list node as a whole object. And so I can point this, I can send this arrow from temp to any point on the perimeter of this box. And as long as it's pointing somewhere to the perimeter of this box, it means that it's a list node pointer, and it's pointing to that object. And then I could use this pointer to get at the fields or the members inside this object. Okay, now what about the string? Without further investigation, I don't really know what's inside the string object. It's possible it includes a pointer. And it's possible it's actually allocating memory somewhere else. And so that this thing is really not stored here. Data is really not stored inside list node, but there's a pointer pointing to somewhere else. Well, the thing is, there's no way for me to know that without going and reading the code for string. And since that's not really the point of drawing the list, I don't really need to represent that string very carefully. So I'm going to exploit abstraction, right? I know that it's something in quotes, I can think of it that way. And I can just draw what the object means inside this box. So when there are details that we don't need to think more about in an example, it's okay to just simplify those details. And so in this case, I'm not going to draw out the reality of what a string object really is internally. I'm just going to use, our C++ principles of abstraction to hide those details and just say, well, I know it's data, and somehow that data gets represented by a string object. And we'll use that from time to time to simplify how we draw things. Again, the thing we want to focus on now is how the linked list works. So I'm going to represent like the next pointers in detail, but exactly what this data is kind of, I'm going to abstract that away because it doesn't matter that much. So let's draw a picture for this code. So I say list L. Okay, so what that means is I'm going to have an object, a list object, and we know that inside a list object, I have a head pointer and a tail pointer. And when I declare an object like this, it's just going to invoke the default constructor, and the head and tail pointer will both be set to null. So this results in kind of a simple drawing. Okay, now let's say I call our append function and I add milk to my linked list. Okay, so what's going to happen is that this append function is going to create a list node object in memory. And then that list node object will contain the milk string and will also be pointing to nothing because it's the only thing in our list. So its next field is null pointer. But now, because I've put milk in my list, milk is both the head and tail of the list. And so now this head pointer and tail pointer are both going to be updated to point to this single list node object. Okay, and then if I append bread, actually I have a problem here, but first let's talk about what happens. So bread gets a node for bread gets created and allocated on the heap. Its next pointer is null because there's going to be nothing after it in the list. But now we need to update milk's next pointer to point to this list node. And what should have also happened is this tail pointer should have gotten updated to point to bread, but I made a little mistake there. I forgot to update it. I think I'm gonna, so yeah, this pointer should actually be pointing around here to bread. Okay, and then let's say I add a little bit more code. I need to add this temporary variable item, and then I also call remove. Well, remove removes the first element of the list and stores a copy of it in item. And so now what I have is this other, object item that's sitting out here in memory, and milk gets removed, and a copy of it is an item, but now bread's the only thing in the list, and so now head and tail are pointing to bread. And here I have head and tail pointer correct. A few more examples. So let's say I have a couple of objects, and I want to establish a link between the objects. Then I may have an object called grocery that's a list. I may have an object that's a list node that I have access to through a pointer called temp. And so how do I make the head of grocery point to this list node? Well, the way I do that is by writing something like this: grocery.head equals temp, right? Because this temp is pointing at list node. If I copy the address in temp into head, then that's like saying the thing that temp is pointing to is, will now be in head. And so head will be pointing to it as well. And so head now, when I copy the value in temp into head, that's going to create an arrow from head to temp. And so this line of code, grocery.head, again, grocery because I'm saying this object was named grocery in our code, and it's a list object. And then to get the head member, I would use .head. And then I would set it equal to this pointer temp, and that essentially draws an arrow from the head pointer to the list node object. And so these two things are now linked together. Now let's say I want the tail of grocery to point to temp. Well, I would do that in the same way. I would say grocery.tail is equal to temp. And so when I do that, it makes tail point to the same thing that temp is pointing to. It doesn't matter where on this box I draw these arrows going to. If they're drawn to the perimeter of the box, they all have the same value. So temp, head, and tail all have the same value, which means I could have achieved the same result by saying grocery.tail equals grocery.head. That would have also worked to give me the result I wanted. In fact, we're often going to find when we're doing these linked list manipulations and you're looking at the code and you're thinking about the code, you might say, well, how come I didn't use this other pointer? Because it's pointing at the same object. So I could have just copied that pointer. And in some cases, that would be fine and it'll be acceptable to do that. In other cases, if the list was organized differently, or if like there was only one item in the list, or there were multiple items in the list, then that pointer you're looking at may in fact have a different value, and then it would be wrong to copy that pointer. And so you always have to think about, what's the pointer that is guaranteed to have the value I want? And a lot of times the best way to guarantee a value you want is to make a temporary copy of it, and then to use that temporary and copy it into the field you need to set. So in this case, using temp gives me a certain level of comfort because I know temp is pointing to list node, and if I want head and tail to both point there, then just using temp to set both of them is the most logical and clearest thing I can do. Even though it would also be correct here to say grocery.tail equals grocery.head. Now, what if I wanted a pointer to the grocery list directly? Like, what if I want something pointing to this list object? Well, I can do that, and I can draw what that looks like. So I would say I have a list pointer, because now I'm pointing to a list. And I'm going to call that G_pointer, G standing for grocery, and pointer just to remind me it's a pointer. And I set it equal to the address of this grocery object. And now over here in my picture, I would represent that as G_pointer with an arrow to this list object, right? And since I'm drawing it to the perimeter, I know it's pointing to this list object. And since it's pointer to a list, it has to have this type list star, right? It has to. There's no other way to represent a pointer to an object other than using that star after the object's name. Okay, then now that I have this pointer to a grocery list, I could say G underscore pointer arrow head or arrow tail to access those fields. Now there's even other stuff I could do, and I'm really just showing you this example, hopefully not to confuse you, but to emphasize that there are a lot of things I could draw here, and that what I draw, has some precise meaning. So I could point to a field in an object as well. I've talked a lot about drawing the pointer to that outer box and what that means, but I could also draw the pointer inside the object. What if I want to point directly to the head field of grocery? Well, then I could do that. I could have a pointer pointing directly at this head. But what would that type be, and what is it? Well, if I take the address of grocery.head, right, then grocery.head is a list node pointer. And so what that means is that this head pointer is a pointer to a list node pointer. And so I need an extra star here. Head pointer is a pointer to a list node pointer. And then this is actually pointing directly at this head field inside my grocery list. And so now when I draw this pointer, I draw it going all the way into the head to reflect the fact that it's not pointing to the grocery object as a whole. It's pointing specifically to the head field in the grocery object, but not somewhere else. So where I draw these arrows really matter a lot. I can make an arrow go anywhere I want it to go just by having the right kind of code over here. But most of the time, we're going to be pointing to these big objects. We're going to be pointing to list node objects, for example. That's the most common thing we're going to be doing. Okay, so in summary, drawing a linked list is a good way to understand its structure and think through the operations on those lists. So later, when we start appending things to lists, inserting things in lists, you might sit down, draw out these pictures, think about how you need to change the pointers, and then write the code that goes along with it. And that can help you understand what's happening in the list. Okay, it's very important to carefully represent the objects and pointers to ensure we understand them properly and that we agree on what that representation means. In fact, you could build a whole language that's a graphical representation that precisely means something in C++ code if you wanted to. Some important details that we talked about: objects or boxes, fields or boxes within objects, with pointers including a black box that serves as the beginning of an arrow. The points to relationship or the pointer relationship is shown as an arrow. Labels allow us to differentiate fields, objects, and temporary variables so that we understand what they are, what they represent. And whatever we draw in a picture can be represented as code and vice versa. And so getting a feeling for that representation, going back and forth, look through the slide again to review it and try it out yourself on paper. And this will help you understand what's going on this semester as we do linked list and as we go into additional data structures.